Hello friends, and welcome to the another lecture on advanced concrete structures. Today we will see the new topic, moments redistribution, or popularly known as the numerical redistribution of moments. Today we will see some short theory to understand the concept and followed by a numerical. So before starting, I would like to introduce myself. I am Amey Khedikar, working in the Department of Civil Engineering at Tulsiramji Gaikwad-Patil College of Engineering and Technology. So we need to understand what is moment distribution. Okay, so I'll read first, then I'll explain. So moment distribution refers to the behavior of statically indeterminate structures that are not completely elastic but have some reserve plastic capacity. When one location yields first, further application of load to the structure causes the bending moment. To redistribute this differently from what a purely elastic analysis would suggest. Basically, it is applicable to statically indeterminate structure that are not fully elastic but have some sort of plastic capacity. When first location yields, the further application of load transferred to the structure cause bending, and to redistribute differently from what a purely elastic analysis would suggest. Going further, when the load is applied to a beam, the beam has a property to resist it. When the beam is indeterminate, it forms sufficient number of hinges to make itself determinate. Hence, in this process, few hinges are formed earlier and rest are formed afterwards. Further, the increment in the load not increase the moment at the points where elastic hinges are formed. The increased load increases the moment in less stress sections of the beam. Hence, due to this, further plastic hinges are formed. In this process, the shift of application of moment in the beam is called as the moment redistribution in the beam. So I hope you understood this. It's a very simple concept that when the load is applied in the beam, in the indeterminate beam, so it forms sufficient number of hinges to make itself determinate. In the process, in the entire process, few hinges are formed earlier and few later on. So further increment in the load does not increase the moment at the points where the plastic hinges are formed. Then the increased load moment in the less stress section of the beam. Hence, due to this process, the further plastic hinges are formed. The entire process of shifting of application of moment in the beam is known as the moment redistribution in the beam. So for an understanding point of view, I am giving an example of beam. Now, a reasonable consideration of the moment redistribution is important for strength design of continuous reinforced concrete beam, at least for the following reasons. It is more economical to allow redistribution of negative moments, and it exploits the ductility of RC beams. In other words, lowering the negative moments near columns allow the possibility of forming inelastic hinges and cracks as a warning of structures operating near the ultimate capacity. Now, what is the reason of doing moment distribution in beam? Why does it redistribute? How does it redistributes? We'll see. The primary reason for doing moment redistribution in a beam is because the moment actually redistribute itself. Okay, and why does it redistribute? Because the moment at the given junction will always try to find a way to become stable. The way in which it does is by distribution and by deformation, call it as rotation. And how does it redistribute? That is depend on the stiffness of the connecting members. Okay, so we have seen the concept of moment redistribution. It refers to statically indeterminate behavior of the structure which is not completely elastic but have some reserve plastic capacities, and it is all about the forming hinges, few earlier, few afterwards. Alright, and the increased load increases the moment in the less stress section of the beam, and due to this, further plastic hinges are formed, and the process of shifting application of moments in the beam called as the redistribution of the moments. And why to do this? It is more economical, allow redistribution of negative moments and exploit to ductility of RC beams. In other words, lowering the negative moments near columns allows a possibility of forming inelastic hinges and cracks as a warning of structure opening near the ultimate capacity. And why? Because the moment at the given junction will always try to find a way to become stable. Alright, and how does? The answer is depend upon the stiffness of the connecting members. So I hope you understood these basics, and until and unless we understand the basic, we are not supposed to start the numerical. And now we'll begin with the numerical.
So friends, now we'll start with the actual numerical. So before starting, I will read first what exactly given data we will try to analyze. A reinforced concrete fixed beam of span 6 meter is carrying an uniformly distributed load of 15 kN per meter over the entire span. So draw the maximum bending moment diagram after 30% of the redistribution of moments. Okay. So it is one of the simplest and easiest numerical to understand the concept of redistribution of the moments. So we'll try to solve the numerical with 30% redistribution of moments. Okay. So I write it here answer, and as we have the given data, so we'll draw the what it has given, the 6 meter span. So we'll draw a fixed beam. We'll draw a fixed beam. Okay. This is of 6, the length will be of 6, length will be of 6 meter, and this is a fixed. Okay, and the UDL is carrying over the entire span of the beam. So the UDL is of 15 kilonewton per meter. So in this numerical we need to carry the diagram after distribution. So I'll just draw the projections here. As it is UDL, so maximum bending moment will be at the center of the this. Okay, so I can tell you there are types of diagram we will develop. First one will be the simply supported bending moment diagram, which will be in kilonewton meter. Okay, and second will be the elastic bending moment diagram, which will be also in kilonewton meter. And then the after 30% redistribution, 30% redistribution BMD. Okay, and finally the combined one, which will be overlapped. Okay, so just in examination also you need to ensure this layout. You need to ensure the layouts so that it is easy to draw afterwards. So in the examination also you ensure the left side page for this diagram and right for the calculations. Okay, so now we will start with the calculation. So our first calculation will be, I can say it as step 1 will be the analysis before redistribution. Analysis before redistribution of moments. Okay, so in that first A part will be calculation for support moments. Calculation for support moments. Okay, so as the beam is fixed, okay, so we'll have moment A, B. Okay, I forgot to just name it. This is A and this is B. Okay, so moment AB equal to F, fixed end moment of AB. Why it is F? Because it is fixed. Okay, so it is minus WL square by 12. So what is the value of W? It is 15, length is 6 square divided by 12, and it is coming to be minus 45 kilonewton meter. Similarly, BA, so fixed end moment at BA was to plus WL square by 12, 15 into 6 square divided by 12, it's coming to 45 meter. Okay, now step 2, calculation for simply supported maximum bending moment. Okay, as the maximum bending moment, as it is UDL, so maximum bending moment will be at the center. So calculation of simply supported maximum bending moment at midspan, okay, at the midspan. So simply supported maximum bending moment equals to WL square by 8. It is the just second part of essay, structural analysis. As it is usually, it is coming to divide by 8. So what is W? 15 into 6 square divide by 8. Okay, so I have a calci also. 15 into 6 square divide by 8, it comes to 67.5. It's coming to 67.5 kilonewton meter. Okay, then okay, so either we can draw all the diagrams in the end, or we can draw parallelly. So what we have done, we have just now calculated the, okay, we'll calculate the third step, then we'll draw the diagram parallelly. Okay, so next step will be step number 3. So calculation of net bending moment in midspan, net bending moment in the midspan. So net bending moment is equals to simply supported maximum bending moment at midspan bending moment minus mod of support moment. When we'll draw the diagram, you will actually understood what is why we take mod. It should not come to negative. So maximum simply supported maximum bending moment 67.5 minus support moment 45. So it is coming out to be 22.5 kilonewton meter. Okay, so now we are done with this. Now we'll draw diagram parallelly. Okay, so as it is the first part, it is the simply supported bending moment. Okay, so it will is also in kilonewton. Units are very important. Okay, so I write it down here. So as it is simply support, so we have the midspan of 45, so it is something here. Okay, it is minus 45. So with the help of scale I will draw here. So it is, the diagram is very important. Valuer will assess the entire numerical from diagram only. So I'll draw an arc. We need to ensure the proper smooth curve. Okay, and it is 45. Okay, it is 45. This is 45. It is minus. It is plus. Okay. And then now the question is, we need to calculate this value. Now how we have done this value, how we have calculated? See here, the maximum bending moment will be 67.5. okay, so the net bending moment will be 67.5 minus 45, so it is coming out to be 22.5. so if you can calculate this right from this to entire this, so it will be 67.5. Get it? Clear? So I hope up till now you have understood this. Okay, and now next step 4 will be calculation of point of contraflexor. It is the point where the bending moment, this distance, it is the point where the bending moment changes the sign plus from minus, or changes sign, that is called point of contraflexor. So we need to calculate location of point of contraflexor in elastic BMD, So actually we need to take this, I need to draw a small beam here. Okay, so this is, I will draw a small beam too easy to understand. Okay, this is of 15 kilonewton per meter. So the beam is fixed, so it is having moments. Okay, and this is your for this you have this section, and that is the point of contraflexor. We need to calculate the value of x. The entire length is 6 meters. Okay, the entire length is 6 meters. So this point of contraflexor, where this, what is the exact distance? Okay, we need to calculate. We also know that it is the MAB, which is 45. This is MBA, this is 45. All right, this we know. Now again there will be reaction at A, this will be reaction at B, so it will be WL by 2, it will be WL by 2. What is the value of W? 15. What is the value of 15 into 6 divided by 2? So it is coming out to be 45. So it is 45, it is 45 kilonewton. Okay, so now what we'll do, we'll take moment about this section. Okay, so we'll take moment about this section. So the moment about this, okay, one step I'll skip. 45x, okay, so this is the in plus, it is going in plus direction. So this 45 into this x minus this is the minus 45, okay, and minus this minus what, this UDL, up to this UDL. Okay, so 15 into x, and it acts at center, so x by 2. So it will be 45x minus 45 minus 15x square by 2. Okay, and moment at this section will be 0. Ultimately we are taking at that point only. So by this way, by this quadratic equation this way, we will get two values of x. One is by solving it 1.27, and second will be 4.73. You can calculate. So you have to choose the minimum value, and you can write it at neglecting the higher value, neglecting the higher values. So with the help of this, we have calculated first the support moments, then the maximum bending moment, okay, at mid span. Then we have calculated this one, net bending moment, okay. Then we have calculated the point of contraflexor. So now we will draw the elastic bending moment, okay, the elastic bending moment now we will draw. So it is also similar to this, but we have now the exact distance. Similarly I will draw here. And this distance will be 1.27. Just now we have calculated point of contraflexor, and point of contraflexor means the point where bending moment diagram change sign. So it is negative, it is positive, it is negative, and this distance will be 22.5. Clear? So this is elastic bending moment, and finally we need to, now this is the calculation before redistribution, okay. Now same calculation we need to do for the calculation, same we need to do for the after redistribution of the moments, okay. So now we will move with the step number part B, okay, or next step, or I can say part, it is first step, I can say part A, and this is the first step. 1, 2, 3, 4 part, and now part B will be the analysis after redistribution of the moments. So we will now start with the analysis after redistribution. So I write it here, analysis after redistribution of moments. analysis after redistribution of the moments. After, okay, so in the numerical it is given as 30%. Okay, so next step number 5. Step number 5, calculation of support moment for 30% redistribution. Okay, that means 0.3. Now MAB equals to MAB of before redistribution 1 minus redistribution. 1 minus redistribution. So it is coming out to be minus 45 into 1 minus 30% means 0.3. So it is coming out to be minus 31.5 minus 31.5 kilonewton meter. Similarly, MBA is equals to moment BA of before redistribution 1 minus redistribution. This is the formula for the after redistribution moments distribution. So MBA equals to plus 45 into 1 minus 0.3 and it is coming out to be 31.5 kilonewton meter. Doing further, step number 6. Step 6, calculation for net bending moment at the mid span after redistribution. So all these steps we have to follow exactly similar, but we need to apply the after redistribution. So I'll write calculation for net bending moment at the mid span, but it is after redistribution of moment. Okay, so net bending moment equals to simply supported maximum bending moment, okay, minus mod of, in order to avoid negative value, support moment. So what is our maximum value? It is 67.5 minus mod of how much it is 31.5 mod to avoid negative sign. It is coming out to be 36 kilonewton meter. Okay, so now we can draw this, but before drawing we must know the actual point of contraflexor. Okay, so we'll now, before drawing it, we can draw right now also, but we'll calculate first the point of contraflexor and then we'll draw the actual our diagram. Okay, so next step will be, so step 7 will be location of point of contraflexor after 30% of redistribution of moment. Okay, so again I will draw the same diagram here. This is your beam A and B, fixed beam. This is A, this is B. So we have fixed moment M A B. You have fixed moment of M A B. This length is of 6 meter, which is given in the numerical itself. This is of 15 kilonewton per meter. Here you will have reaction at A, here you will have reaction at B. Okay, and this is the section where this will be the X. This will be the X. Okay, how much you have MAB, which is equals to 31.5 31.5 is minus, and this will be 45. I hope you understand. WL by 2 equals to 45, WL by 2 equals to 45. So now we'll calculate here. Now we will calculate here. We'll calculate. So we'll take moment about this axis. So mx, moment at this section x, equals to minus, it is minus, okay, 31.5 minus 31.5. This is minus in anti-clockwise, so it is minus. Now what is clockwise? This 45 plus 45 into x plus 45 into x, and this UDL minus, this UDL is minus 15 into x dx by 2. So the equation will be 45x minus 31.5 minus 15x square by 2. So you have got the quadratic equation. Okay, so now there will be two values of x. So first value of x will be, so we can solve in the calci also. So if you can put the value in calci, I can generate the equation, that is 45 into x minus 31.5 minus 15x square by 2. So solve for x, it will be 0.81. okay, and again go with this, and we will say neglecting higher values, So now we have got the point of contraflexor 0.81. So now we can draw this diagram. So now we will draw the diagram. So we can draw the diagram, but now we will draw at the top. It will be negative. It will be, so this will be 31.5. This, okay. So this distance we have got now 0.81, and this also we have calculated, which is 36. So this is minus, this is plus. In this diagram, both the diagrams are same. You can draw down or upward, it's okay, but don't make a mistake in terms of sign conventions. So bending moment always in negative. Okay. So by this way we have calculated the analysis after redistribution, where we have calculated the calculation of support moments. So support moment of the actual part into 1 minus 0.3. What is 0.3? It is 30% after redistribution. Then just like a moment of AB, BA, then calculation for net bending moment. This we have calculated the 67.5, which is the maximum bending moment for simply supported case, minus the fixed support moment. It is coming out to be 36, and then we have calculated the redistribution moment, the contraflexor, point of contraflexor. So this is the point where the bending moment changing its sign from negative to positive. So it is 0.81. We have calculated also point of contraflexor. So, and finally we have drawn this diagram. Okay. So the final part of the numerical is remaining, in which we will cover now the calculation for bending moment before redistribution of moments at the point of contraflexor. Okay, and after the redistribution of at 0.81 meters. Okay, that is M dash. So now we'll see in the next part. So step number 8. Calculation for bending moment before redistribution of moment, at the point of contraflexor, and after redistribution of redistribution at x equals to 0.81 meters. So we need to calculate the maximum bending moment before redistribution but after the point of contraflexor after redistribution, that is in bracket called as the m dash. Okay, so now we will draw that given, that is A, this is your beam. Okay, this given as 15 kilonewton per meter square. Okay, this is point A, means you have reaction at A. This is point B, means you have reaction at B. This is WL by 2. This is WL by 2. It is 45. It is 45 kilonewton. This length will be 6. All right. Then you have the point of contraflexor at 0.81. This distance will be 0.81. We have calculated after redistribution, at the point of after redistribution. Okay, so you have moment also, so MBA and MAB, it is 45. And now this moment you have to take before redistribution. Okay, before redistribution, kilonewton meter. Okay, so now you have to take the moment. So moment at x equals to, okay, now you know the distance with what is, so this is the 45 into x, so 45x, okay, minus 45, this minus wx square by 2. What is w? Your 15. I can add directly as 15, no problem. So this is the m dash, okay, because your mx at 0.81. So at this point we are calculating it, so it is m dash 45 into 0.81 minus 45 minus 15 into 0.81 square divided by 2. So your m dash comes 2, it is minus 13.47 kilonewton meter. So it is coming to, so what we have done, we have taken the section here, this is 0.81. we have just now calculated the point of contraflexor after redistribution of moments. Okay, and we have now calculated the actual bending moment of before redistribution of moment but using the point of contraflexor distance of after redistribution of the moments. So m dash we have calculated. So last step, step 9, last step, which stands about value of m dash, that value of m dash. So m dash stands for the moment after redistribution. M dash after 0.3 means 30%. Redistribution of moment. Redistribution of moment. So it is coming to m dash into 1 minus redistribution. So it is coming, what is the value of m dash? Just now we calculated, minus 13.47 into 1 minus 0.3. So it is coming out to be minus 9.43 kilonewton meter. So this is the value of m dash. So this is the of m dash, and it comes to the calculation for bending moment before redistribution at the point of contraflexor after the redistribution. So we need to take the redistribution, the point of contraflexor value after redistribution, but moments of previous, before analysis, before the application of redistribution of moments. So this is by this way. In step 9 you will get, in step 8 you will get the calculation point of contraflexor, and in step 9 you will get the value of m dash. M dash is nothing but the value of maximum bending moment after the application of 30% redistribution of the moments. So I hope you understood the numerical and all the steps are clear. And before again concluding, I would like to revise once again. So this is the numerical we have completed. This is the simply supported bending moment diagram, okay, where the support moments and the calculation for maximum bending moment at the midspan we have done. Then we have calculated the point of contraflexor. This is all about the before the application of 30% of redistribution of the moments. and this is the diagram after the application of 30% redistribution of the moments. This is the BMD, and finally we need to draw here the merge diagram of the both. Okay, so we have this diagram, you must draw by scale. Okay, so I'll manage the scale. Okay, not visible. So you have this 1.27, so it will be here. Okay, just to focus how I'm drawing it. So it will be 1.27, where it is the bending moment, so it will be negative. Then you have 0. So 0. Your next after the application of the moments, it is coming out to be 0.81. So it will lie some here. So it is the 0.81. So this will be the distance 0.81, 0.81, 0.81. Okay, and from this you have this 36, then here 36. So from here you have this. Okay, so this way we need to, this is plus. So by this way your final diagram will be that's okay. So it will be also elastic bending moment. It will be also elastic bending moment after 30% of redistribution of moment. Distribution of moment. Okay, distribution of moments. So then we have calculated this. Then after redistribution, we have calculated the support moments. Okay, then 1 minus 0.3. Then after we have calculated the calculation for net bending moment at midspan, so it was coming out to be 36, and then we have calculated the point of contraflexion, which is coming out to be 0.81. So by this way we have calculated the analysis before redistribution, analysis after redistribution, and finally we have again drawn the calculation for bending moment before redistribution. So for bending moment we need to calculate before redistribution by using the point of contraflexor of after redistribution. Okay, that will be m dash.